So we are starting conic sections. This first section is just kind of a broad view over what conic sections are in general. And then we're going to look at each type of conic section one at a time and really be detailed about what the equations look like and what the graphs look like, etc., etc., etc. So the first thing is, why do they call it a conic section? And it's called a conic section because you have a cone. You see the two cones kind of stacked up, and you can cut these in a variety of ways. You can cut it so you have a circle. You can cut it so you have a parabola. You can cut it so you can have an ellipse, which most of us would refer to as an oval. Or you cut it so that you get a hyperbola. And a hyperbola is basically a pair of symmetric parabolas. Okay? So that's why they call it a conic section, is it's how you can cut two cones stacked like this to get these different two-dimensional figures. So even though they're coming from a three-dimensional idea, our focus in the chapter will be in 2 dimensions, those 4 shapes. We are talking about conic sections. What is the graph of x squared plus y squared equals 16? What are its lines of symmetry? What are the domain and range? So in looking at that equation, this is an example of a conic section we should recognize. Can anybody tell me what two-dimensional figure that equation represents? So this is one that you may or may not, some of you it sounds like may not, remember from geometry, but the basic idea for an equation of a circle, which we're going to go more in depth on that later in the chapter, but it was x minus h squared plus y minus k squared equals r squared. Look familiar? So this equals radius squared equals 16. 16 is what squared? 4. Now how do we know that we don't include negative 4? Because a radius is a length, and so we don't worry about the negative 4. So we know this is a circle of radius 4 centered at the origin, which if we remember this from geometry, hk is the center of your circle. What are we subtracting from x and what are we subtracting from y? 0 each time. So the center of the circle is 0, 0. Our radius is 4. So when we graph this, we're just going to go to 4 everywhere. Like that. So it is a circle with radius 4 centered at the origin. Right, when given in this form, the center of your circle would be the point HK. And that is kind of the depth we're going to go into later in the chapter for each conic section. I only bring it up for circles here because it's something you should have seen last year. So there should be some level of familiarity here. But we have the rest of this question. What are its lines of symmetry? So for a circle, how could I draw a line through this circle that cuts it in half? So the main idea for lines of symmetry for a circle, basically any point or any line that goes through the center. For a circle, now my hand-drawn circle doesn't look the greatest, but for a circle we should all be comfortable that if you draw any line that passes through the center of the circle, that is cutting the circle exactly in half, which is what a line of symmetry is supposed to do, make it symmetrical. Hopefully, from looking at the graph, you can see the domain. X needs to be between negative 4 and 4. Range, same thing, but for y. Just from looking at the graph, the x's go from negative 4 to 4, the y's go from negative 4 to 4. which is something that would help us with domain, for example. You could solve for y. You would get y squared is 16 minus x squared. So y is plus or minus the square root of 16 minus x squared. And you could get your domain analytically this way. Analytically just meaning not looking at the graph, but looking at the equation. You would have to remember that since there's a square root here, you know that 16 minus x squared has to be greater than or equal to 0, which means that the absolute value of x has to be less than or equal to 4, which is the same thing as this. X has to be between -4 and 4, including both endpoints. So the last one was a form that looked familiar to us. This one is not. Okay? If you could rewrite it in the form we had on the last problem, x squared plus y squared equals a number, that's a circle. We can't do that here because what we could try is divide each side of the equation by 27. That would give us x squared here, but it would not leave us with just a y squared. So since we have two different numbers here, I'll tell you that this is going to end up being an ellipse. But how are we going to go about graphing it? We could choose to rewrite this problem as 9x squared plus y squared equals 9. Yeah, if you divide everything by 3. And that we could not rewrite in the form of just x squared plus y squared as a number. And because we cannot do that, we know it's not a circle. So what we could do is we could say y squared is 9 minus 9x squared. Then we know if we take the square root, it's plus or minus the square root of 9 minus 9x squared. And as he pointed out, if you want to do that in the calculator, your calculator doesn't have a plus or minus button. So what you would want to do is you'd want to say y1 is the square root of 9 minus 9x squared, and y2 is negative square root of 9 minus 9x squared. What we should get is, as we just heard, points at 1, 0, negative 1, 0, 0, 3, 0, negative 3. And it's going to look like this, which is an ellipse, or what we would call oval, but it's an ellipse. Lines of symmetry for this one, unlike the circle, which had an infinite number, how many do we see here? 2. The lines of symmetry are the axes, the y-axis and the x-axis. And that's it. Okay, so the two lines of symmetry, x and y axis. What about domain and range? We'll do that looking at the graph again. What's the domain from looking at the graph? The x's can only go from -1 to +1. The range, the y's are only going to go from -3 to +3. So, if you see an equation that's x squared plus y squared equals a number, or you can rewrite it into the form x squared plus y squared equals a number, that's a circle. If it's x squared plus y squared, but the x and the y squareds have different coefficients, but it's still addition, then you should know you're dealing with an ellipse. If it's something in the form like this, where you've got the y squared minus x squared, or flip it around, you could have an x squared minus a y squared. If it's subtraction that's happening, then you know what we have is a hyperbola. And a hyperbola is basically like two parabolas that are mirror images of each other. That's all we're really looking at here. So how do we get the graph? Let's do like we did in the last problem. Y squared is x squared plus 36. So y is going to be plus or minus the square root of x squared plus 36. And then again, how do we make our calculator give us something like that? Tell it to graph the positive as well as the negative square root of x squared plus 36. When putting this in the calculator, we are able to see that we have points at 0, 6, and then it's kind of a big fat parabola. And then points at 0, negative 6, and another big fat parabola like this, where again, these should be mirror images. It's exactly the same. This one's opening up, this one's opening down, but the shapes and everything, they should be reflected across the line y equals 0. Which is a hint, what are its lines of symmetry? Again, this one has 2. And those lines of symmetry are the x-axis and the y-axis. So just like in the last problem, lines of symmetry, x and y-axis. Which goes back to the question we had before, are these always going to be centered at the origin? Today, usually yes. When we look at each conic section in depth, then we're going to move it around and those lines of symmetry will move with them, as you would imagine. What about the domain and range? Domain here could be anything.
Oh, okay.
And you should be able to see that from the graph, going all the way in either direction, but also looking at the equation we came up with. We need x squared plus 36 to be greater than or equal to 0. X squared is always positive because it's squared, or 0. And you're always going to add 36. So you could plug in all real numbers here. What about my range?
It's also anything.
So the range, y has to be less than or equal to negative 6, or y has to be greater than or equal to 6. So we have the graph, we have the lines of symmetry, we have the domain and range. The domain in interval notation would be this. The range in interval notation would be this. So, two types of conic sections are represented in this figure. Equations that are possible models for this figure include those three equations. So looking at the figure, what two types of conic sections are represented? We have a circle, several of them. Okay, the black dots, those are circles. And then we have the things around them, those are ellipses. So, circles, ellipse. Which equation is a possible model for the object in the middle of the figure? Right, Chaw. Okay, for part A, x squared plus y squared is 196. Again, because we know it's a circle, so we need an equation that can be written in the form x squared plus y squared equals a number. And of these three, the bottom one is the only one that can be written in that form. Coincidentally, it already is written in that form. Part B. What is an equation for a possible model of the paths of the small circles? So we have 36x squared plus 9y squared equals 324. Because if there is addition here, but we cannot rewrite it in this form, x squared plus y squared equals a number, where the coefficients are 1 both times. If the coefficients are going to be different, we know that's an ellipse. And the third equation here with subtraction present, that's going to be a hyperbola, which is not represented in the figure at all, so we get to just ignore that one. So, the main point of this example is how do you take these three types of conic sections we just looked at, and looking just at the equation determine, is it a circle, is it a hyperbola, is it an ellipse? So are there questions on how to do that?